let's finish up this example from the previous video. And we will also, in addition to those computations, get a new concept going. We'll get a new theorem. How exciting. Okay, let's start with this system from the previous video. And we have now 3 different ways that we could write this thing down, but they all really mean the same thing. They're literally just different notation. And all 3 of them end up getting solved so far the same way. Our only technique so far is to put it in an augmented matrix and go to the row echelon form, or the reduced row echelon form, even better. And you certainly should still be able to do one of these by hand. We are getting to the point, though, where we're going to want to focus on other things and let the technology do some of the grunt work. So this is the point where I want you to start finding some way that you can do reduced row echelon form on a calculator of some sort. If we were doing this in the classroom, I would be using a TI-84 calculator because that's what most of my students have and everyone has one in the classroom. With the online class like this, I haven't quite figured out the best online app for doing this. Right now I'm going to use one called Microsoft Mathematics. It's a free application. I'm almost certain there's better ones out there, so find the one that works for you. And if you find a better one than what I'm using, please let me know. I find that my students generally are very good at ferreting out the best tool out there. So I would love to use a better tool. So let me know what you find. But for the moment, I'll use Microsoft Mathematics, and I'll try to remember to put a link to it in the module. So let's go ahead and tackle this augmented matrix. Let me go ahead and erase the other forms here. We don't really need these anymore. So we'll just solve this one using reduced row echelon form. Let me get Microsoft Mathematics pulled up here. So this is what it looks like. Microsoft is not developing or supporting this anymore, but it still works just fine. There's sort of a basic graphing calculator on the left and a worksheet on the right. Tools for different subjects within math. We're here at linear algebra. And we, at the moment, want to reduce. So reduce, and we want to insert a matrix. Let's see, we currently have a 2x4 matrix. So we'll say, okay. They tell you down here you can type all this stuff in without clicking if you're more of a keyboard person. But anyway, let's go ahead and type this in. Let's see, I've got 2, 5, 1, 3, 1, 3, 6, 2. Okay. And I want to reduce that, so I'll just go ahead and hit enter. And this will take this all the way down to reduced row echelon form. And we can see how it comes out. So I'm just going to jot this into our whiteboard over here. So negative 27, negative 1, 11, 1. I think that was right. I'm going to double check here in a minute because my brain, as much as I would like it to be, is not infallible. Let's see, where was that? Negative 27, negative 1, 11, 1. Yep, perfect. Okay, so there's our reduced form. And if we want to go ahead and write down solutions, this first line now, put x's and whatnot back on, says x1 minus 27x3 equals negative 1. And of course, we usually like to solve for each variable individually. So I'm going to go ahead and move that 27x3 to the other side. So say 27x3 minus 1. Okay, so there's the first line solved for x1. I'm going to do the same thing, solve the second line for x2. So normally it would say x2 plus 11x3 equals 1. I'll move the 11x3 term to the other side. So there's x1 and x2, and of course, for sake of completeness, I like to write down what x3 is, which is, it's a free variable. So I typically just write x3 equals x3. And we see there are solutions to this matrix. There are infinitely many solutions to this system of linear equations. Pick any number you want for x3, and you will get a solution that works here in the original equation. Notice that we had two pivots. So the pivot positions are right there and right there on the original matrix, which gives us, of course, two pivot columns as well. The fact that there are pivots in each row means that we have solutions for x1 and x2, and that anything beyond that, any columns that are not pivot columns, are just free variables. So we had one free variable at x3. So the fact we had a pivot in each row means that there will be solutions. And matter of fact, let's step back and contemplate that just for a second. So this is theorem 4 from your book, and it points out that we can make 4 different statements that kind of match our 4 different forms here about whether or not there's a solution. So let's take a look at each of these statements in turn. So it says, first of all, let A be an n by n matrix. And what they're talking about here is the coefficient matrix. They're not talking about the augmented part. So when they talk about A, they're just talking about this much of it. It says, then the following statements are logically equivalent. And let's be careful about what that means. That means for a particular A, either all 4 of these statements are true, or all 4 of them are false. So if you find one of these to be false for a particular A matrix, then you know the other 3 are false as well. It turns out as we go on throughout the course, we're going to build onto this theorem. There's going to be multiple equivalent statements, and it'll be very useful to know just if one of those is true, that they're all true. We'll get a lot of information from just knowing that one of those things is true, or false for that matter. Okay, but let's look at our 4 statements. So one of them says, for each B in Rm, so keep in mind of our different forms here. The B comes from this matrix multiplication form, and I guess I'll jot this back down. I probably shouldn't have erased it. It's 2, 5, 1, 1, 3, 6. That's A. This is X, X1, X2, X3. And B was the vector on the other side. 3, 2. It says, so for every B, every possible 2-dimensional vector you could think of, the equation has a solution. So it's not just that it's 3, 2, but we could find a solution if this was 100, negative 17, or 1,563,212 and 0, or any vector in R2, you could find a solution. So it says, if that's true, so is this. That each possible B right here, is a linear combination of the columns of A. And again, keep in mind what linear combination means. It means that you could write this as some multiple of the first column plus some multiple of the second column plus some multiple of the third column. 1, 6. So really that's just our vector equation form, saying our vector equation form and our matrix equation form are equivalent. If you can find solutions with this form, you can also find solutions by combining the 3 columns of the matrix. C says that's also equivalent to saying that the columns of A, so again, these are the columns of A, which are also right here. Those columns span R2 in our case. And keep in mind what span means. Span says everything that you can reach by combining these. So if the equation has a solution for every b, that means you can get to everywhere in two-dimensional space, and you span all of R2. So all three of those are basically saying the same thing. D says that if A has a pivot position in every row, so pivot position in the first row and a pivot position in the second row, that's equivalent to these other three statements, sorry. So if you know that there's two pivots in your two-row matrix, you know that there's solutions. You know that there's infinitely many solutions. There's a solution for every possible thing you could try to write over here. And hopefully that kind of makes sense with this 3-2. Right now that we know there's a pivot here and a pivot here, if I change this 3-2 into other numbers, there'd be other numbers showing up here. But that wouldn't change the fact that solutions exist, right? All it would change would be this part of the solution. But I could still write down a solution. The fact that there's a pivot in the second row means there's no way I'm going to get a 0, 0, 0, 13 or something over here. That's what a no solution looks like. And then there's no pivot in the coefficient matrix. All right, so all four of those statements lock together. And if we know one's true, we know they're all true. If one's false, they're all false. And we will make extensive use of that throughout the rest of the quarter. Trust me, you'll get sick of this particular theorem before we're done with it. But it's going to be such a useful tool for us. All right, a little bit more in the next video, and then you'll be ready to tackle the homework.